Welcome back all. So last lecture we saw that if a differential equation is exact, then what condition it should satisfy and how to solve. There were two different approaches to solve that problem, but now the question is that if a differential equation is not exact, then how to make it exact, because we know how to solve exact first order ODE. So here in this lecture we will see how to convert the non-exact first order ODE to exact first order ODE. So first we have to see that the differential equation of the type mxy dx plus nxy dy equal to z equal to 0 is said to be exact if del m by del y equal to del n by del x. But our aim is that if del m by del y is not equal to del n by del x, then what to do? Then we will try to multiply some factor to this equation and make it exact. So what we will do? So again this differential equation we will reframe into different terms. So if I write p in place of m of xy, so p dx, and in place of n if I write q, so it will be q dy. This is nothing but only the notation. So if this is the differential equation where this condition is there, means non-exactness. So what we will do? We will multiply f is the factor, both the sides of equation 2. Then what will happen? Then the differential equation will be f p dx plus f q dy equal to 0. So we are assuming that after multiplying f, we will get the exact differential equation. So this will be equation 3. So if this is exact, okay, then what will happen? This will be termed as m and this will be termed as n. Now if this is exact, so exact condition will be satisfied. So del m by del y equal to del n by del x. That means del by del y of fp equal to del by del x of fq. Here there are two approaches. What is the approach? So that we have to see. Okay. So if I take, if f is the function of x only, then what will happen? The left side will be fyp plus fpy, right side will be fxq plus fqx. Okay. Now as our factor f is the function of x only, so what will happen? This will be 0. If this will be 0, the left side will now becomes only fpy equal to fxq plus fqx. Now we have to arrange all those things. So if we arrange, so what will happen? So we will take f of x right only and the fqx will take to left. So it will be fpy minus fqx equal to fx q. So this again we can write it as fxq equal to f common py minus qx. Now this again is equal to what? Fx by f equal to 1 by q times py minus qx. So what we want? We want f. So what will be f? How to find? Now this fx by f is there, and here it is right side the expression is there. What we will do? We will do integration both the side with respect to x. So fx by f dx, right side will be integration of this same term with respect to x. So it will be into dx. Now if I take integration of this, so what will happen? It will be log f, and the right side will be same thing. I will write now. If I remove the log, how to remove? I have to take exponent. So finally f will be exponent e to the power integration of 1 by q times py minus qx dx. So we will get this factor. Okay, and this is nothing but the integrating factor that we will use in Bernoulli equation. So this is how we find the integrating factor. Now another thing is that if here we have taken f as the function of x only, if f is the function of y only, then the factor will change. Only the factor will change. So f will be what? E to the power integration of 1 by p times, and inside bracket it will be qx minus py into dy. So this is the expression, okay, that we will get when we have y, when we have f as a function of y. Now here one thing we have to note that this py nothing but del p by del y, and qx is nothing but del q by del x. So in this way we can get the factor f, which we multiply to the equation, this equation 1, and make it exact. So we have taken equation 2 as non-exact, and we can make it exact. Either we can take f as a function of x or f as function of y. As the problem demands, we will take those type of factors.